E chi la vedi questo streaming? No, per qualche indirizzo web?
Beh, possiamo iniziare?
OGS.
Allora, buongiorno a tutti.
Grazie Michele.
Sì. Grazie per essere qua. Oh, English, sorry. I have to change language. So sorry. Thanks for coming, and also for our host that came from Mexico, a long way. And as you know, this workshop is part of the bilateral project between Italy and Mexico. And Laura will give a brief introduction about what this project is. And then right now I will give the floor to our president, Maria Cristina Pedicchio.
Yes, thank you very much. Just a few words. So welcome all of you, mainly to the people that are coming from further away. So welcome also from the colleagues from Dubrovnik. Yes. And thanks a lot to Vanessa and to the other colleague for organizing this meeting and for following the project. I think that we will be connected with who? With
we will connect it later because it's 5 o'clock in the morning.
Okay.
It's a little bit early.
So for our new guest, I think it's your first time in Trieste, is it? Yes. So just a few words about our institutions. So OGS, this name stands for National Institute of Oceanography and Experimental Geophysics. So we are national, that means that we're working under the aegis of the Ministry of University and Research, and our main field are ocean and geophysics, as is the name. We are organized with 4 departments for scientific and technological section that are oceanography, infrastructure, geophysics, and seismology. So we also have a very active section of seismology with a location in Udine, that is a city nearby, in 1 year in Trieste. Then I think that with respect to university context, I'm a university professor, so with respect to academia, what is characterizing research centers, but mainly OGS, is the fact that research centers are managing great big infrastructures. So research infrastructures. You will have time to discuss with the colleagues that are here, but OGS is owner of a research vessel that did 11th, I remember well, campaign to Antarctica and a few campaign to Arctic. So it's dedicated to polar area as well as to Mediterranean one. And now we are in the situation of buying a new one, mainly dedicated to Antarctica research. Then not only a research vessel, but a research plane, but then a glider. How many gliders do we have now? 4. 4 gliders, different kind of ocean observation system. Vanessa is the expert, so we will get all the details from the colleagues. But for OGS is doing research, is doing a lot of services for private companies, services for civil protection, and all our activities are related research, innovation, education, and user infrastructure. So research infrastructures is really what makes the difference from an education center like university. And you can know more details about that. Concerning our main activities, I don't enter the details of the program, also because I'm a mathematician, so I'm in a different field. But our strategy, our vision is based on what the big fashion at European level, what is called now mission-oriented attitude. So research and innovation, mission-oriented priorities. So there is this new word mission that for the European Commissions for Europe now is really the key word in research programs. Missions coming from the Apollo missions in the state. What was a mission? We send a man to the moon, but then we want this man to come back safely. So missions means we have an objective, very high, very ambitious objective, defined time, in how much time, how much money. So things must be clear. What we want to do, why we want to do, when, with which money. But mainly this notion of missions. Missions are somehow the societal challenges. But missions include that the results must be obtained thanks to interdisciplinary and intersectorial research and public-private collaboration. So the emphasis, but this is a characteristic of OGS, working in a multidisciplinary approach and with a private component. So mission must be developed together with different institutions, and there must be a strong impact on society. This is another key word. Mission means impact. So the point is that research must have an impact on society. And for OGS, again, this is a priority. Another field of research, for many years, it was not a priority. Also in mathematics, we are doing our theorem, but who cares of the impact of society? Those things are different. Impact is very important. And when we say impact, means into citizens, impact to society. So we are looking for the effect of research on one side on economic aspect. So research must support the economy, must support creation of jobs, must support creation of blue jobs in your area. So economical development, but social development. So there must be a great attention, mainly in the field of marine and maritime research, on the social aspect. That means also on the sustainability, that subject that you know better than me. And I would like to say on responsibility of all of us, researchers, but citizens, but private businessmen, on responsibility in managing seas and oceans. And missions are, in a very, as I said, very ambitious approach, considering all these aspects. So OGS is building is a research program that I'm saying also for my colleagues, since we will present in 2 weeks, we will present the new 3-year programs, and it will be again built on 5 missions: knowledge of seas and ocean, polar research, risk management, so on. And this, I can say, is really reflecting what OGS is, a mixing of people from different backgrounds, strong collaboration with companies, with services, and strong attention, as I said, to research infrastructures and to people. So attention to researchers is for us a priority. We try with the difficulty of laws, but we have developed a program also for female researchers. We have many, a general director that is female, president that is female. So we have this program for supporting recruitment, for supporting young people, to valorize mobility, incoming and outgoing. And we got from the Commission the acknowledgement of excellence in human resources. I don't know if we are really excellent, but in Italian difficult context, we are doing our best. So human resources is a priority. And I would like to mention last things that OGS is doing a lot in the field of so-called science diplomacy. Science diplomacy is another of the key words at international level, probably also in your countries. And we are developing specific program in higher education and training for Mediterranean regions in responsible, sustainable blue growth. Science diplomacy, that means that we are supporting researchers and also people working from ministries and so on, other institutions coming from North Africa, so the south side of Mediterranean. And I don't know if in your country there is this idea of science diplomacy, trying to put together people coming from different geographical regions. But here in the Mediterranean, with a very complicated situation that in your country you know very well, we have realized that working through knowledge and through researchers, we can get much better results also in terms of dialogue, in terms of more peaceful context, more than just working with classical diplomacy or with ambassador. And we are doing master, summer courses, many activities that some of you here participated. But these things of science diplomacy nowadays, with the difficulties that our world is living, geopolitical difficulties, science can play a very important role also in this field. So I wish you a very interesting stay and fruitful stay in Trieste, and thank you again for coming.
Thank you.
Welcome to everybody. I will just describe to you the project. The project has a strange name, as always Vanessa says to me, but I always say her that it is the sound is similar to the names of the goddess, the Aztecan goddess, so it's something related with this project. Anyway, this is a project within the Italian-Mexican bilateral program that started this year and will finish in 2020. And it is sustained from the Italian and the Mexican Foreign Ministry. This project is part of the sector, the macro sector climatic changes, and its title is this one. It is in Italian because it's a bilateral project, Italian-Mexican, is sharing of knowledge and methodologies of analysis of the data for characterizing the oceanic variability at different scales, the vertical migration of zooplankton and the carbon fluxes in the southern Adriatic and in the Gulf of Mexico. And the keywords are mesoscale, because we are looking for mesoscale phenomena, zooplankton, vertical migration, and carbon cycle. The Italian institute is our institute, and the Mexican one is the CICESE, the Centro de Investigación Científica y de Educación Superior de Ensenada, that is located in Ensenada in Baja California. The researchers involved in this project are here. This is the Italian part, and this is the Mexican part. Today here we have Miguel Tenreiro and Enrique Payas, that perhaps you have already known. Miguel and Enrique, they are here, and this project started as a mobility project that was just intended to cover expenses for traveling of the researchers, but then it had an upgrade of the project, and we could also organize and pay for a person working on this project, and also organize this workshop and trying to share and to see if we are able to continue with this collaboration and to continue the research within these two institutes. The area are the Southern Adriatic and the Gulf of Mexico, where the Mexican researchers work. And the processes we want to study are the vertical migration of zooplankton, and its link with the vertical transport of nutrients and carbon. And the second process is the passage of mesoscale eddies and their role in the vertical propagation of the inertial waves, the mixing, and the transport of nutrients and organic matter within the water column. The data available at the moment on which we have done our studies and research together are the 12 years of data of the Southern Adriatic site, the H13A, and then there are more than 11 years of data acquisition from the net of moorings in the west part of the Gulf of Mexico and data gliders. Then the colleagues from Mexico will explain better
which is their type data set. The methods are described in this publication here, and we're trying to exchange methodology and trying to apply the methodology one to the data of the other, and so on. In particular, the data set, maybe you already know which kind of data are part of the Southern Area GUI site, and we have current from which we calculated the index scattering strength from the ADCP that covers this layer, the surface layer. And then we have currents at bottom, temperature, salinity, oxygen, and transmittance, particularly from sediment tracks at different depths. Then there is a buoy also, which measures the atmospheric parameters together with these parameters at surface. Moreover, we have used also the biological data, in particular zooplankton and chlorophyll from the Institute for Marine and Coastal Research of the University of Dubrovnik. And in this workshop, we have here Rade Garic that collaborated with us on these with the zooplankton items. And finally, there is a set of oceanographic parameters from the cruises. The data set in the Gulf of Mexico, they have many current meters at different sites with currents, then there are temperature, oxygen at different quotes, and then the glider data with current, temperature, salinity, but we will see in detail in a few times later on. The objectives of this project are in particular to exchange methodologies and used to analyze physical and biochemical data set at different scale, the comparison of the processes in the two areas that are different from some points of view but are similar from other points of view, and then we want to consider the multidisciplinary study in the Southern Adriatic as a case study that can be exported in the Gulf of Mexico or to other areas in the world. And we want to also try to construct a multidisciplinary conceptual model to study the carbon fluxes within the water column. And we want also to look for long-term trends and variability in the data set that are present and trying to relate them to climatic change on a global scale, looking if they are present on both area. And also, we wanted to, we are looking for a possible future integration of the results in prediction models. And we hope to have the possibility to continue the collaboration, to have a future project together between the institutes. And that's all from as a description of the project. And this is the program for today. Now we will listen to Enrique. We'll have two talks on the Gulf of Mexico and the measurements there, and then we will have a coffee break before connecting to Mexico via Skype when it is a reasonable time for them, and we will listen to their
Speech. Yeah.
Okay.
Thank you.
Okay, thank you.
So
You have to skip the.
I apologize, but I have to go.
it's
Sorry.
okay. Thank you.
Ya. Ah, muy bien.
Lo haces una vez, ¿no? Es mejor si te pones un dedo con esto.
Okay. Espera, no era la apertura, no. Okay. Is that one, ¿no? No sé qué dice. ¿Anula?
Anula.
Perfecto. Okay, then I'm gonna start my talk today. Thank you very much to be here in this little workshop that Laura and Vanessa organized. And thank you for inviting us here these days. My name is Enrique Payasar. I work in CICESE, that is in Ensenada, north of Baja California, south of San Diego, California, the real California. No? And well, this work, I'm going to talk today about the loop current eddies, are mesoscale eddies, so are scales of 100 kilometers, and a lot of characteristics that we found from different measurements, different instrumentation that we use in the Gulf of Mexico. This work is in collaboration with a lot of people, Miguel that is here in the room, and other postdocs and students, 3 groups that work in Mexico. This is Connect group, it's the mooring group. It's a group with a lot of experience with moorings. They have 32 moorings and continuously measuring the western side of the Gulf of Mexico for more than 5 years, 6 years actually. And then there is this other group, GMOC, that I'm leading, and it's a group of gliders. Es Grupo de Monitoreo Oceanográfico con Gliders. So we measure the ocean with remote technology, if you want. And then the GEOLA is another group that uses drifters, surface drifters. So there are drifters that are drop either 1 meter or sometimes 15 or 50 meters depth. So I'm going to go further. I'm going to talk a little bit about, I don't want to spend a lot of time in this slide, but this is some classification of mesoscale eddies. Well, mesoscale, as I said, these are eddies that have horizontal scales 100 times larger than the vertical scale. So there are lengths, very thin lengths. No? So mesoscale, this ratio, it's more equal, so that the horizontal scale and the vertical, it's only 10 times. So mesoscale, we're talking about an area of 100 kilometer radius and 1,000 meter depth. So it's 100 to 1, okay? So we can have anticyclonic eddies, cyclonic, anticyclonic. We have a vertical structure with isopycnal sloping downwards, and a cyclonic eddy, we have it sloping isopycnal upwards, okay? We can also have warm eddies, cold eddies. We have intrathermocline eddies that are eddies that are subsurface. They can have signature, surface signature or not. And this classification, anticyclonic, cyclonic, as we know, depends on the sense of the circulation. Anticyclonic eddies are clockwise, and cyclonic eddies are counterclockwise, the currents. And then we can classify also the eddies if there is one eddy or 2 or structures with 3 eddies. No? This we talk about monopole, dipole, when we have 2 eddies together, or tripole, we have 3 eddies together. So we have different classifications. The eddies that I'm going to talk about, it's anticyclonic mesoscale eddies with a superficial signature. So this we call loop current eddies. So here, I don't know why it doesn't run that. No, here maybe. No. Well, there is no movie. Maybe because I passed the presentation from Keynote to PowerPoint, so I don't know. But this was a movie. Here I'm showing the Gulf of Mexico. This is absolute dynamic topography. It's the surface scale, but it's another variable. In red colors are the sea surface. It's elevated, and more green colors. The sea surface. It's a depression of the sea surface. So we have anticyclonic eddies on red. We can see the surface currents that are on the clockwise sense, the red structures, and we have the green structures are cyclonic eddies, so the circulation is counterclockwise. Okay, so the Gulf of Mexico is a kind of a mesoscale turbulent sea, enclosed sea, with a lot of anticyclonic eddy that detach from this current that we call the loop current, Yucatan current, Florida current, and we have this anticyclonic loop. So at times there is a process of detachment, and these eddies are detached from the loop current and propagate westwards towards the western side of the Gulf of Mexico. So what we can, or how we can study these eddies, we can study the surface signature of these eddies with satellite imagery. It's public satellite data. Here it's SST from this satellite, and we can see that these structures are warm structures of more than 30 degrees or more than 25 degrees, and also are structures with a lot of salinity, high salinity. So are large structures, warm and salty. What more we can see from satellite? We can see that these structures, these anticyclonic eddies, are like biological deserts. So they are within like oligotrophic waters. There is no much chlorophyll at surface, at least, because we will see that there is chlorophyll, subsurface chlorophyll. No? So we can see, we see that very clean waters with these chlorophyll A modies inside the anticyclonic eddies, but we see some small cyclonic eddies with chlorophyll inside. That these ones are called loop current frontal eddies, small eddies that are on the front.
Can you see, because since we are recording, no, on the other hand, you have to be there.
Closer.
Yes, like this.
Yeah?
Yeah, because we are recording.
Okay. Okay.
Okay.
Yeah. And also we can see like through the true ocean color, also we see that there is no much signature of chlorophyll or pigments. Like here we can see, but not inside the eddy. Again, the movie it's not working. Sorry about that. Maybe after I can show you these movies. This is like a different. This is a figure. I'm gonna focus on the right figure. This figure that it's a composite of thousands of trajectories. And so what it's condensated in this figure, it's each of these circles. It's a colored circle. If each of these circles are like particles or drifters, this one of these drifters, that it's doing a closed trajectory. So when the drifter gives a closed trajectory, we can draw one of these circles, and the color, it means if it's a cyclonic trajectory, or anticyclonic, it's blue. So what we see here is that there are these anticyclonic blue eddies, that these large loop current eddies that are detached from the loop current and propagate westwards. It's this signal, this blue. And then we have three regions of cyclonic eddies, small eddies. These are the Tortuga eddy, that are eddy that forms around this Key West on Florida. And we have this Campeche eddy, it's a large cyclonic eddy. And also we have this, the Americans call this like a platform cyclonic eddies that are those region, red region. So well, we have a lot of eddies. And what's the importance of these mesoscale eddies in the Gulf of Mexico? The important thing is that these eddies transport large amounts of salt from the Atlantic Ocean and also of temperature. Here I'm showing this transect from the west side of Africa to the Caribbean Ocean. This is this section. This is depth, and this is the longitude. So what we see is the Atlantic subtropical underwater, very salty, that it's formed on this side of the Atlantic Ocean and sinks as it's propagating westwards. So this core of high salinity, it's sinking and propagates towards the Caribbean. So when this salty water arrives to the Caribbean, it's transported by by the Yucatan current inside the loop current or inside the Gulf of Mexico, and eventually these eddies detach and transport these high salinity cores towards the west. At some point it's going to dissipate and contributes to the salt budget in the Gulf of Mexico. So here in these two panels, I'm showing salinity and temperature from different Argos. These are the colors. One Argos here, here, here. So different Argos through the Yucatan current, and we see the signal of this subtropical underwater high salinity core, subsurface salinity core, how shallows and propagates towards the Gulf of Mexico. And also here we see that this water is very warm water, so salty and warm water originated on the North Atlantic, and that it's transported towards the Gulf of Mexico. This can be observed with this climatology that one of our postdocs did using a large database of different cruises of opportunity and different public data. And all these red dots are glider data from GMOC. So combining all these databases, she come up with this climatology of salinity. This is absolute salinity TO10 and the conservative temperature at different depths, 100 meter depth, 200 meter, and 800 meter. And what we see is, again, we see like a salt region, that is the region where the eddies. This is the most common trajectories of these loop current eddies. So through this trajectory, we see salt waters and warm waters and salty, especially at 200 meter depth. That is the depth of the subsurface salinity maximum. So clearly have a very strong impact on the thermal structure in the Gulf of Mexico, these eddies. So are very important. Using different data from moorings, this is all these stars. It's the moorings that are deployed on the western side of the Gulf of Mexico of this group Connect. So what we did, this is the typical structure of these eddies. This is a very deep eddy with four ADCP long rangers and warhorse and different current meters, point current meters, and thermistors. So it's a strongly or heavily instrumented mooring, especially the deep ones. So with this data and with a method to detect the eddies, like we use this Chenot et al. 2009, that allows us to detect the periphery and the center of the eddies. On red, I'm showing the anticyclonic eddies detected with this methodology, and on blue are the cyclonic eddies. So what we do, it's a methodology combining satellite and mooring data to come up with a lot of observations within anticyclonic eddies and within cyclonic eddies. We have 6 years of data, of mooring data, so we can have many profiles within anticyclonic eddies, and we combine all these profiles to come up with a climatology, with a composite, like an eddy composite, a mean structure of a mean anticyclonic eddy and a mean cyclonic eddy. And what I'm going to show here is just some statistics that come up from this eddy detection. So once I detect the eddy, I can compute the radius and its mean eddy kinetic energy, surface eddy kinetic energy, and its Rossby number or normalized vertical vorticity, also at surface, because this is from satellite data. And I'm comparing the loop current region that we have some moorings and the western Gulf of Mexico region, and compare the eddies in terms of radius, kinetic energy, and Rossby number. What we see on the loop current is that the cyclonic eddies have larger Rossby, it's these blue cyclonic eddies, and red are anticyclonic. So the cyclonic eddies on the loop current region have larger Rossby numbers and larger kinetic energy and similar radius. It's here we have similar radius. We have larger eddy kinetic energy on the cyclonic eddies and larger Rossby numbers. And by contrast, on the western side of the Gulf of Mexico, both cyclonic and anticyclonic eddies have similar parameters, similar radius, similar kinetic energy, and similar Rossby number. So the loop current eddies, when they are on the east side of the Gulf of Mexico, are more energetic than when they are on the western side of the Gulf of Mexico. That makes sense because they travel for almost 9 months, 1 year. They can be traveling to the west, these eddies. So they lose energy, they decay with time. But this is pretty much what we find. So here I show some TS diagram. Again, for the loop current region, for the western Gulf of Mexico region, this is again a composite TS diagram. This comes up from combining 5 years of mooring data and satellite data. So what we find here is this subtropical underwater salinity maximum at depth. It's here at 250 meters. That it's not present on the anticyclonic eddies on the western side. This red line is inside anticyclonic eddies, and the blue line are inside cyclonic eddies. So on the western side, there is no the salinity maximum, and it is on the eastern side. This is because this salinity maximum, it was eroded during this propagation, during several months. It's gonna get eroded. And we're gonna see through what is the mechanism, that it's the winter convection. That's similar, well, here in the Adriatic, it's huge, it's 2,000 meter depth. There we have convections until 140 meters, 1,000 meters depth. Yeah. So, and the cyclonic eddies, what we see, it's on the loop current region. They are pretty cold eddies, because they entrain water from an upwelling from the Yucatan Channel. I'm not going to get in this process, but here there is an upwelling. This is Yucatan, and here is the Yucatan current, and here is Cuba. So there is an upwelling, and these cyclonic eddies that form in this region, they entrain this upwelling water. This is because they are very cold. And on the western side, again, what the result we obtain is that similar water masses, the two diagrams are parallel, are two lines, but if you see, they are just shift on depth. And this is because the inner structure of the cyclonic eddies, you have upward isopycnals on cyclonic eddies and downward isopycnals on anticyclonic. So I obtain the same water mass, but at different depth, 100 meter depth of shift, because this sloping, but we have the same water masses inside both eddies. And here these mean profiles of temperature, salinity, and speed. And again, red anticyclonic eddies, blue cyclonic eddies, and again the differences between western and loop current. Loop current is continuous line, and western side is its dashed lines. So we see the eddies, anticyclonic eddies are warmer than cyclonic eddies, and saltier than cyclonic eddies, and are stronger or with larger speed. And also we can see that if we compare dashed and continuous line, we see that on the loop current are warmer than on the western, are saltier than on the west, and are faster than on the west. So again, the same conclusion, the eddies when are young or are just detached from the loop current are warmer, saltier, and more energetic. So we also can survey or measure these structures with gliders. We use the sea glider. This is a buoyancy AUV that the physical principle, it's just changes of volume and changes of buoyancy through pumping oil. So what we obtain, it's like a upward and downward movement with this pump, and with the wings, we get the horizontal displacement. And with the rudder, we can get also some with the rolling batteries and moving them forward and backward, we get the pitch or the roll to control the direction on the horizontal movement. So typically, what the glider does, it's like these trajectories, like a zigzag on the vertical, and they measure any sensor you can put on them. No? They are platforms, and then you just put any sensor you want, and it's not too heavy because you need to ballast. So we have a limitation on ballasting, but you can put different sensors. We typically use a wet lab Seco triplet for optical measurements, a CT and pumped conductivity and temperature of Siebert, and an oxygen sensor, and we have an A2 DCP for measuring currents. So here, what I'm showing is one of our best missions, I say, because we measured this Luc Purreneri Poseidon. These Luc Purreneris that are detached, and there is an Enterprise Deep Horizon Marine that put names, like the hurricanes on the Atlantic, that they have names, and these eddies also have names. So this one is called Poseidon, and well, we were measuring Poseidon for its lifetime. For 1 year, we use a glider and we follow it during a year, 4 missions of 3 months each mission. So we were measuring continuously this eddy. What are the pros of these gliders? It's autonomous and flexible. We can change the trajectory, and if we see a bloom of chlorophyll, we can come back and survey again and do different transects. We can focus on some structure. So it's a very flexible. It's autonomous. We can pilot from our house. You can have very high resolution and study processes from mesoscale to small scale, and we obtain the near real-time data. Okay, so if we lose the glider, we still have the data. This is super important, no? Because what it costs money, it's the data. So pretty much in 2-3 missions, we already paid the glider because we really, the data is so expensive to get with a vessel. So you cannot collect water samples, you cannot see the microorganisms, all of that. We always need the ship, but I'm very, very excited to use these guys, and really I think they are gonna substitute a lot of research on the vessel, like CTD and physical measurements. These guys are much more cheaper than getting out there with a ship. So this is what we obtained with these 2 sections. We did a section from south to north of this Poseidon eddy, and this is a second section from northeast to southwest. We crossed the eddy. Here we were running behind the eddy because he started to propagate westwards, and the glider was very slow propagating platform. It's 0.3 meters per second maximum, 0.2 meters per second. 20 centimeters per second without thruster. We don't use thruster. We don't have a little motor like Slocum. And so we don't get that fast horizontal movement. This eddy moved at the same speed. So we were behind the eddy trying to cross it. So well, this is the first section of, this is a T anomaly, this temperature anomaly, salinity anomaly for the first section, and this is for the second section. What I want to highlight here is that these huge temperature anomalies of 9 degrees. That means that the eddy, it's 9 degrees warmer than the Gulf Common waters. So, and also we have that it's like 1 PSU saltier than the Gulf Common waters. So are a huge monsters of 9 degrees warmer and 1 PSU warmer than the surrounding waters. This is huge, you know. And here, this works. Here I'm showing the glider, how it is crossing this eddy Poseidon. This is temperature, salinity, and density. So we're getting inside the core, and we see this salinity maximum at depth. typical of subtropical underwater, very warm structure, a mixed layer, very warm mixed layer in summer. It's more than 30 degrees. So here we're getting out of the eddy. Here getting in a small cyclonic eddy. The isopycnals are sloping upwards. And then we come back and we do the southwest section. And here you're gonna see that we're trying to chase the eddy and it's propagating almost at the same speed. But the cool thing of that is that we're getting this data every 5 hours. We get on our computers a profile. So we're getting the data on near real time. No? Okay, so through this section we measure temperature salinity, so we can measure with the C-state equation. We can measure the density, and from density or gradients of density we obtain geostrophic velocity. So the geostrophic velocity across the section, and are these two sections, depth and distance, for the first section, for the second section, and we see these scores of high velocity on the periphery of the eddies as usual, are cores of 1.5 meters per second, and here 1 meter per second. This we need to take it with caution, because depending on how we cross the structure, if we cross fast or the structure is stationary or not, we're going to have a lack of synopticity. So this is a big problem with glider, because glider propagates very slow, and if the structures move fast, we're not measuring right the gradients, because if I travel with the structure at the same speed, I'm going to be measuring the same water mass. I'm not going to measure any gradient. And if we go once against the other, what I'm measuring too fast gradients, overestimating the gradient, because the two structures are moving one each other. So that is very important. And we come up with a correction, but it's very difficult because we don't really know what's the movement of the structure with the satellite. We have one image per day, so and we neither know very well how the glider moves under the water, so it's difficult to correct that. And what about the stratification of these eddies? We have a summer conditions on the left panel and winter conditions on the right panel. This is the vertical derivative of the density, potential density. It's a kind of Broom by Sala. It's not Broom by Sala because there is no gravity and density, but it's vertical gradient of density. So we here see on summer a double thermocline structure with a summer thermocline at 50-meter depth and a permanent thermocline near 250 meters. And here there is a thermostat, that it's a well-mixed and homogeneous water within the core of the eddy. What happens through winds and winter mixing? This is convective mixing. What we obtain is a very well mixed layer, very deep. Well, very deep, it's 140 meters here. And we see here the permanent thermocline, okay? So the winds broke this summer thermocline and mix all this thermostat with the mixed layer waters. In summer, one starts the heating. What we obtain is the opposite process. So this is reflected on the mixed layer climatology or mixed layer yearly evolution on winter and January, February, and we obtain very deep mixed layers. This is inside anticyclones and inside common Gulf water, but what I want to stress here, it's deep mixed layer in winter and shallow mixed layer in summer, okay? And this is through this winter convection. And what's the effect of the winter convection on this salinity maximum? This is on the top panel, salinity evolution, 4 missions of the glider. This is mission 3, 4, 5, and 6. This is sections within the loop current eddy Poseidon. This is a year of measurements inside the eddy Poseidon, salinity, and here temperature. And what we see, it's an erosion of this signal of subtropical underwater, a very salty core, and it's eroded with time. This is winter, it's December, January, February, the salinity maximum shallows, and also it starts to decrease, to dilute. It gets diluted. And also, well, here what we see in temperature is the year cycle with summer warm, winter colder, and again summer warm. Okay, but what we are interested in this process, what is the most, or what is the cause of this erosion of salinity? To answer this, we did some simulations with NEMO. So we did a realistic simulation of the Gulf of Mexico, and we just target one of the loop current eddies detached from the loop current, and we follow it from its detachment to its dissipation on the western side, and we started to look at the salt budget inside the eddy to see what are the most important terms on the salt budget equation. So here I'm showing this salt budget equation. This is the local term. Sorry for the equation, but and this is an advection. This is advection of salinity, horizontal, vertical advection of salinity. This is the term of horizontal diffusion of salt, vertical diffusion of salt, surface processes, evaporation, precipitation, runoff, and a residual. It's an error that comes up on when you compute a salt budget between a structure that is changing on volume, because the eddy it's not always the same eddy. So you're doing this budget on a volume that is changing on time. So we have a few errors here. And here I'm showing for the life of an eddy. This is 2 years. This eddy lasts for more than a year and a half, and I'm showing all these terms. This is the time evolution of all these terms as a function of depth. This is the local, horizontal advection, diffusion, and what we see that the local trend is very well explained with the vertical diffusion. You can see this, and these panels are exactly similar, are very, very similar in the first upper 250 meters. You can see that the vertical diffusion is the term that explains the local term on the first upper 250 meters. So why this term is important, and when this term is important, we see that this term is important where we see that there is a dilution of salinity. It's the blue colors. Blue colors means loss of salt, and red colors, it's a gain of salt. So what we see, it's at the base of the mixed layer, that it's this line dashed magenta line. We see the winter, summer stratification, and winter again. There are 2 winters, okay? And what we see is on the first winter, we see this entrainment of salinity, this blue line, and this on surface layers we gain salt, and on the bottom surface salinity and subsurface salinity maximum we lose salt. So what we see, it's an injection of salt from the salinity, subsurface salinity maximum to the mixed layer, and the mixed layer is gaining salt, and the maximum it's losing salt. This is the same idea, but these are mean profiles for different periods, spring, summer, autumn, and winter, and 2 years. And this is for 25 numerical eddies. So we did a composite using to make it a statistic, more robust, statistically. Well, and we did this composite of several eddies, numerical eddies. And what we see is for the young eddies, this is the maximum of salinity, typical maximum, The eddy can be detached on spring or on summer, are young eddies with a strong subsurface salinity maximum. And we see on the first winter, the black line, it's the vertical diffusion, and the red line, it's the salinity profile. What we see on the first winter is that we have a very negative, strong negative vertical diffusion of salt, that what does is to erode this subsurface salinity maximum, as we see on the following months. The first winter, deep vertical convection, erosion of the subsurface salinity maximum, and we see more homogeneous vertical profile of salinity on the following months after the first winter. And to end, I want to say that these eddies have a signal on the first 1,000 meter depth. So here I'm showing a time series of a mooring. Okay, this property, it's the Rossby number on colors. So red colors are cyclonic vorticity and blue colors are anticyclonic vorticity. And what I show here, it's a lot of structure on the first 1,000 meters. These are the signals of the loop current eddies. And on the bottom, what we see, it's a more homogeneous signal. And these are very deep and homogeneous eddies that we believe are traveling together with the loop current eddies, surface loop current eddies. So we have very, very deep eddies on the bottom from 1,000 meter depth to 3,000 meter depth. This is a deep cyclone, deep signal of anticyclone that are traveling beneath these loop current eddies. I'm not gonna get more in detail. And also what we found is on these large loop current eddies, we find intrathermocline eddies, smaller eddies like satellites that are embedded on these larger eddies and turn around the large eddies. It's like the Earth and the Moon. So we have subsurface small eddies that are traveling around these large eddies. This is the first time that has been observed, this kind of eddies in the Gulf of Mexico traveling around the larger eddies. These eddies, if we do a zoom of this small, this is stratification. So these eddies are low stratification cores. And what we see is the sloping isopycnals on both upward and downward, typically of an intrathermocline anticyclonic eddy. And we see this stream function. These contours are stream function, and we see that it's an anticyclonic eddy with velocities of 0.2 meters per second. It's fair enough. This eddy has been observed for the first time because the glider has a very high resolution measurements. So before we start to measure with the gliders, probably we maybe can do a cast on the eddy, but the next cast is 5 miles away, and there is no more eddy because it's a submesoscale eddy. So you need a very high resolution and continuous measurement. That is something that offers you the glider. And I'm going to end up just saying something about vertical velocity on these eddies. Vertical velocity on these mesoscale eddies, it's very complex, depending on the initial structure of the eddy, but we can have like quadrupolar structures like this one, when we have a single ellipsoid of one sign of potential vorticity. We have a dipolar structure of vertical velocity. That means this is upwelling, this is downwelling on blue, and on red it's upwelling. And this appears on spheroid isolated eddies. What means an isolated eddy? It's that has a core of one sign potential vorticity and a ring of the opposite sign of potential vorticity. On this kind of eddies, because of the tilting of the main axe, what we obtain is a dipolar structure of vertical velocity. What is clear is that in the center of the eddy, and now I'm talking to the biologists, because sometimes there is this misunderstanding that in the core of the cyclonic eddies there is upwelling. and in the anticyclonic eddies there is downwelling, and this is not true. Usually in the center of the eddies there is zero vertical velocity. When you obtain like positive vertical velocity, it's when you have what we call eddy pumping, and eddy pumping means a cyclonic eddy that it's enhancing, or it's getting stronger. So because it's getting stronger, the isopycnal slope, or an anticyclonic eddy that is getting weak. Because it's getting weak, also the isopycnals are sloping. This is what it's called eddy pumping. And when an eddy is enhancing or weakening, you can have vertical velocity in the center. But if it's an eddy that has some energy and keeps this energy, it's not enhancing or decaying, the vertical velocity in the center is zero. So the strongest vertical velocities is at the peripheries of the eddies. So this is an important thing. The blooms pretty much are going to occur on the peripheries of the eddies. And this is a numerical model, and we can see on a realistic simulation of the Gulf of Mexico several patches of upwelling, downwelling, upwelling, downwelling, and on the vertical also. So the vertical velocity is pretty complex. It's not that simple. Cyclonic eddy upwelling in the center, anticyclonic eddy downwelling in the center. And there are many cells of positive and negative velocity. The important thing is the vertical velocity is 4 orders of magnitude smaller than horizontal velocity. So pretty much the plankton is going to turn horizontally, but a little bit it's going to go down. But it's 4 times smaller. If we have 1 meter per second, a particle turning horizontally 1 meter per second, and vertically it's 0.0001 meter per second. So on the vertical. So it's not going to sink or well much. And thank you very much. I talked too much. Huh? I don't know if you have any question on these eddies or something about this. Yeah.
How do you compute the mixing layer depth?
It's with the temperature criteria. It's 0.5 degrees. I try different with density criteria, with temperature criteria. It doesn't change much unless you have a freshwater plume.
Mm-hmm.
When you have freshwater plumes, sometimes we get wrong measurements. Also, we can measure the mixed layer depth using optical measurements. With backscatter, usually the backscatter is going to drop on the base of the mixed layer. So it's a very nice proxy. We obtain with the glider data, with the backscatter data, it's a very nice proxy of the mixed layer depth. Yeah. But there are many criteria, and it depends on, I don't know, sometimes I use one criteria or the other. Yeah.
Any questions? Can you show when there was a profile, there was an erosion of this. Please, in the young eddies. So there is the force. In that case, there is the losing.
Here.
Yeah, there is maybe okay. The reason is also after that you have the mixing. In this case, so it's losing, but it's also maybe there is a redistribution of salt.
Yeah, there is a transfer of salt from here to the upper layer. Yeah. So if you see here, finally the upper layer is much saltier than here. All this maximum, all the salt here, it basically passed here. It just it's entrained on the upper layers, and here it's eroded, and on the upper layers it increases the salt.
Yes, but in this equation, I think, do you consider the transfer of the mixing due to the wind or to convection? Or
well, actually the wind gets in here.
Yes.
On this coefficient, yeah. So on this coefficient, you need mixing, you need the energy that comes from this coefficient, and you need a vertical gradient of salinity.
Yes.
So the vertical gradient of salinity comes because this maximum, it's here. This is a strong vertical gradient of salinity. And also we have winds and strong eddy viscosity. So we have both things working together, but I don't know, we did not measure that. This is all modeling.
Yes,
So it's model.
it's not real.
We suppose to
Huh?
get
Real numbers.
Real number. That because you can associate it with the real, and the environment to as we have for the mixing that occur during the convection, the real, and you have the effects of the Bora in that case. That you have the mixing, and this not only constant, but it is just as a the wind gust, and then you have very locally in time for a couple events, really events, but those events can really contribute to change the whole structure of the eddy. In that case, just one small depends on the certification that we have, and then okay, so maybe depends on how much does the event can mix or can get more mixing or transfer of salt.
Yeah, this is a composite of a winter. So of the first winter for 16 eddies. So this is a composite. So on the composite there are many events. Okay. So this is not just one event. This is a composite of many winters. So when in the next presentation, I'm going to show you that it's true events. Yeah. Okay. We're gonna see on a single winter, and we're gonna see that this is it's events of wind. Yeah.
Okay. Yeah. Thank you.
Yeah, I wanted to ask you, in the first slide you showed so different chlorophyll inside the eddies. Some were really oligotrophic and some not.
Yeah.
Which is the reason?
Well, in that case, inside the anticyclonic eddies, these large eddies, loop current eddies, they were oligotrophic, because when we will see next that on summer there is the chlorophyll maximum, it's deep chlorophyll maximum. So all the chlorophyll is at depth. So there is no chlorophyll on surface waters. But on cyclonic eddies, these small cyclonic eddies, they usually have larger concentrations of chlorophyll. And probably it's because they also advect, they form over there locally, and they advect chlorophyll from the coast, from the platform many times, and train chlorophyll. But on terms of vertical velocity are the same. On terms of vertical velocity, a cyclonic eddy or anticyclonic eddy have the same distribution of vertical velocity. Can be dipolar or quadrupolar, but they have the same. So you should not have a criteria to say why in one it's more chlorophyll than in the other, because it's the same vertical velocity. So should be something of horizontal entrainment or local production, because the injection of nutrients. I don't know much about the metabolism or the biology.
Okay, let's go.
Go ahead. Yes. So which one is the?
L'altra dietro?
Maybe you like better that one.
No.
It's more about chlorophyll.
¿Te acuerdas de estar parado allí? Porque si no...
Aquí ya me olvido.
Es que si no, parece que uno habla solo de amor.
So well, then I'm gonna continue with this other talk. It's the chlorophyll distribution during the life of the anticyclonic loop current eddy Poseidon. It's that eddy that was detached. So we did 4 missions, LiDAR missions following it, and I'm gonna present some data, chlorophyll data within these eddies. I presented this talk on the last Ocean Science and submesoscale session. So well, First, to talk about a little bit of the sea gliders and the sensors that I'm going to use, or the data that I've used for this presentation comes from the sea gliders, specifically from a Seabird CP sail. It measures at 1/5 of airs. It's one sample every 0.5 meters. And the measurements are from surface to 1,000-meter depth. And we are sampling during diving and surfacing. And then we also use this Wet Labs Eco triplet that measures chlorophyll fluorescence. I'm not going to talk about production. I don't want problems. I'm going to talk about chlorophyll. So I don't know about production, but it's a proxy apparently, no? But it's not that straight, no? So I'm going to talk about chlorophyll and variability of chlorophyll, okay? So this is pretty much what the glider does on the column water. It does dives of 1,000-meter depth, and we obtain one profile every 5 hours. We obtain more or less four profiles per day, because it's 1,000-meter depth
Short question.
diving. Yeah.
And what means that you measure chlorophyll? Is a sensor for chlorophyll, or
It's optical sensor, yeah.
Okay.
So it measures at some wavelength. Yeah. Yeah. So this triplet has 3 different wavelengths. So one is to detect the chlorophyll concentration, the other one backscatter, and the other one is sedum. That is
We have the
organic
same
dissolved
control as
carbon.
carbon.
Yes. So these are the data sets. This is the first mission. This we already saw these sections. This is the first section of Poseidon, and then the second section. This is the second mission. We lost the GPS in the middle of the mission, so the glider start to drift. We call this drifting section. It start to drift inside the eddy, and we were able to recover it, but we lost the control. But it remained inside the eddy and drifting. So we obtained nice data inside the core of the eddy. Here are some of the I resume or some of the characteristics of each of these missions. It's not that important. This is the third mission that I'm going to present. That was 2 sections through Poseidon. That was already an old Poseidon, because it's already on the western side. Here was in the central Gulf, was younger, and here it's already an older Poseidon. And here also we measure an old Poseidon. No? So this was summer, winter, autumn, and again summer. So we have a year of measurements. And again, the movie, I will show you some point. Yeah. Again, this stratification, because this is relevant to explain the chlorophyll distribution within the eddy on summer and winter. So here I want just to stress this double thermocline structure on summer and this well-mixed deep layer on winter. So again, this is the 2 sections. This is the first section of Poseidon, second section, again, stratification. This black line is the line of density of, I think, 1,025, where we will see later, well, we see already. This is the chlorophyll on these 2 sections. This is the chlorophyll concentration on color, and we see that pretty much the deep chlorophyll maximum, it's very nicely following this line of 1,025 of density. This is because the nutricline, it's somewhere starts over here. So we have the plankton likes to be very close to the food and where it has enough light. Probably you know more than me, but what we obtain on summer, where it's very stratified, we have the deep chlorophyll maximum within the eddy, this thermostat. This is because it's the periphery. On the periphery of the eddy, we have this sloping isopycnal, so also the chlorophyll is sloping, it's shallowing. And these red dots show the depth of the mixed layer. So we see that it's stratified, summer stratification, deep chlorophyll maximum. What happens on winter? Already start the wind and start the convection. This is 16th of December. This is within the eddy, red dots. Already we see the depth of the mixed layer. It's 150 meters, more or less. So very deep mixed layer. And what we see is the chlorophyll. It's not anymore concentrated on a deep chlorophyll maximum. Now it's distributed on over the mixed layer depth. So, but what we see, it's a clear subsurface maximums. It's not that I have. It's not just mechanical mixing. There is a local enhancement of chlorophyll. What means that there is some injection of nutrients, because if I compute the mean or the integrated chlorophyll, I do not obtain the same concentration than before. So there is injection of nutrients, and here is what you, Vanessa, were explaining me about these events. If you see, we have different events.
Yeah.
1, 2, 3, 4, 5. These different events. These are different wind events. In the Gulf of Mexico, we have these cold fronts on autumn and winter called nortes that come from North Carolina, from United States, and these cold fronts last for 3 days and cross all the Gulf of Mexico. So you have these events, nortes, and each of these intensifications are related to a norte. So if we see satellite data, also we see on the third mission, we see like oligotrophic Poseidon, young Poseidon, and on the western side, on December, on the mission 4, we see already some patches of chlorophyll within the eddy that it's in agreement with what we observe with the glider. So it's an anticyclonic eddy, but due to these wind events, we have injection of nutrients and enhancement of surface chlorophyll. Here I'm showing the mixed layer depth with 2 different criteria, on blue and on red, and on black it's the depth of the chlorophyll maximum. So what we see here is time, and this is depth. This is the 4 missions, glider missions, and we see summer, like a very shallow mixed layer, winter, a deep mixed layer, no? And red and blue, 160, 150 meters, and summer again, and shallow mixed layer. And what we see is the chlorophyll maximum, it's well beneath or well below the stratification, so it cannot be mixed. But in winter, we see that the mixed layer depth and the chlorophyll, reaches the base of the chlorophyll maximum. So the convection reaches the depth of the chlorophyll maximum and injects nutrients and distributes also the chlorophyll through the first 150 meters. And again, in summer stratification, and again, the deep chlorophyll maximum. So this is some distributions across the eddy. I could come up with some relationship between the depth of the deep chlorophyll maximum and the isopignal of 1024. This is nice linear relationship. I can come up with an equation. So knowing the depth of the isopignal, I can know the depth of the chlorophyll maximum. That it's interesting because I just need to do physical measurements to know where the plankton is. I don't need to measure actually the chlorophyll. Only measuring the density, I can obtain where is the chlorophyll maximum. And also I can see on the mission third, I can see that this relationship applies if I do a scatter plot of absolute dynamic topography that I compute from satellite, and the depth of the chlorophyll maximum, I obtain a relationship. that tells me that within the core, that it's high absolute dynamic topography, and pretty much there is no relationship. It's flat, there is no correlation. And for the going to the periphery, I obtained this nice correlation between absolute dynamic topography and the depth of the chlorophyll maximum. That makes sense because on eddies, smaller eddies or weaker eddies with small absolute elevation, sea surface elevation, have also small depression of the isopycnals. So the deep chlorophyll maximum is shallower. On weaker eddies, the deep chlorophyll maximum is shallower and than stronger eddies. And what about the temporal evolution or distribution of chlorophyll? Here I'm showing again a time series, but now it's a depth average chlorophyll, or I think it's integrated chlorophyll. I mistake here, but this is the integrated chlorophyll because it's in meter square. So integrated chlorophyll between 0 and 200 meter depth, time, and here it's the value of the integrated chlorophyll. This is surface chlorophyll, time, and this is the different missions, mission 3, 4, 5, 6. And on the bottom panel, I show the magnitude of the wind on a buoy very close of the glider measurements. And what we see is that we have a seasonal cycle, pretty much. Pretty much we have a seasonal cycle. We have a low integrated chlorophyll on summer. Then we have an enhancement on winter, and again, low integrated chlorophyll. And here we can see clearly these events.
Yeah.
This is like peaks.
Yeah.
That means that there is injection of nutrients. The plankton reacts to this injection, grows, and then eats all the nutrients and falls again. And then comes another event of wind, again, injection of nutrients, the plankton grows and falls, and again, up and down and up. We have these events. And these events match very well with the wind events, pretty much. And there is a delay between the maximum wind and the maximum chlorophyll concentration. Probably it's because the organism needs some time to grow. But what we see is a nice correlation between the wind bursts and the increasement of chlorophyll. And here I'm just doing a spectral analysis. This is the spectra of the chlorophyll concentration, and this is the spectra of the winds. So we find different frequencies. We find like a peak on 24 hours that can be due to the sea breeze, maybe, or to near inertial waves that in some way modulate the chlorophyll. We don't know. But the important peak on chlorophyll, it's around 7-8 days. That means that these peaks occurs every 7 days, every week. And this matches with the peaks of these nortes, of these wind events, that it's pretty much 7-10 days. So there is a high correlation between these peaks on these frequencies and the wind frequency peaks. No? And well, the conclusions, we have oligotrophic deep chlorophyll maximum extreme on summer. So we have this chlorophyll maximum and the nutrients are trapped beneath this strong stratification. So the plankton is trapped well, it's located at depth. And then in winter, we have this eutrophic DCM extreme, that the chlorophyll maximum is shallow. There is nutrient-rich upper euphotic layer because there is injection of nutrients. So there is a growth, new production, and well, the chlorophyll is controlled by the input of nutrients through energy inputs from episodic wind events. Thank you very much.
Any question? Pussy. Biology.
Yeah, it's good.
Of course, I imagine that you have no data about the species that form chlorophyll during your experiment.
No, I don't know.
But even from previous studies in the area, because
There are probably, but I did not.
because what is quite strange for me is that you don't take in account that the chlorophyll is produced by different organisms that can profit of different conditions. There are organisms that like mixing waters, so can like better, like diatoms, for example, in winter for us. So probably diatoms in your mixing period. Other organisms that can survive or have a better life in stratified waters with less nutrients.
Mm-hmm.
And the quantity of chlorophyll produced by the cells is different.
Yeah. Yeah, it's what I said at the beginning. I'm not. I'm just
just
going to
if
talk
I-
about the chlorophyll. I don't know where it comes from the chlorophyll. What are the organisms who produce this chlorophyll? I just studying the variability of the
But the
chlorophyll.
variability, of course, will be driven by major forcing like either dynamism or nutrients, but also by the species.
The kind of a
composition.
species, of course. Yeah. I imagine, yeah, but when I'm just studying, I'm just seeing that it's an enhancement or decreasing or increasing,
Okay.
and I don't care if it's
And the
one
second
species or the
question
other
is-
species.
Something about the penetration of the light during different periods. But in summer, you have deep chlorophyll maximum that is very low. And have you any measurement of the penetration of the light in that period?
You mean that here in these conditions on summer?
Yeah,
I didn't. No, I
but you
didn't.
can have it.
But
Your instrument measure also the light or something?
No.
Some proxy of the light?
but in the Gulf of Mexico, it doesn't change much.
We are really in lower latitudes, there is not enough.
There is a different than we have for the long daylight, they're almost the same.
Yeah,
They
it's
have,
almost the same conditions during summer and winter.
Light conditions. Yeah.
No seasons.
No
2
seasons.
hours maximum. No, it's not.
No, I'm sorry, not the duration of the light, but the intensity of the light, where the light arrives. Because
It doesn't change too much in the southern
It's quite identical between the summer and winter. There is a seasonality in the temperature, but you can see any other seasonality unless in the atmosphere.
But you have water that is different, that in winter is
But just for
is well
the,
mixed, and in summer is stratified. So probably also the properties of the water change a bit, so the penetration of light change.
Yeah, for sure, yeah, probably.
And you are supposed to have normally, probably in summer, if there is nothing, because apparently there is no chlorophyll in surface, I imagine that the light can arrive in deep, more than in winter. I was just asking if you are on light.
Talking about
talking
light.
about like,
Yeah, this is summer, and the light penetrates at least here because there is chlorophyll at 130 meters.
And
So-
it's also lower.
So the light penetrates here, and I will think that in winter in winter can penetrate even more, I guess, because there is no stratification. No? We did not measure that the penetration or the profile of the attenuation of the
Maybe
light.
you have algo floats with radiometers around, so you can get from there.
Yeah, there are argo floats. Yeah. Probably we have a colleague that did a work, similar work, but he did with argos, and actually he come up that there was no an annual cycle of integrated chlorophyll. He obtained that there was no cycle, and we with the gliders we obtained that yes, there was a seasonal cycle, and we believe because was a lack of sampling with the argos. because we did not
In this
measure.
sense, I think it's important to know also par data, photosynthetic instrumentation. Have you some data about this parameter
No,
in order to know the radiation of the light, because it's very low.
But part you
Yeah.
can have it from
Exactly. Photosynthetic,
yeah.
in order to compare also the
Uh-huh.
radiation of the
Thank
light
you.
and photosynthetic, and is also characterize the species, if is monospecific or all the community, in order to know this very high, not very high, but it's important to know this in terms of biological trophic change.
There are groups in this consortium, because this work it's part of a large consortium in the Gulf of Mexico that are doing all that stuff. But we did not meet still, biology is doing their stuff, physicists is doing their stuff, and then we're gonna try, we're gonna start to discuss together, because they did a lot of stuff with the species, with SAR, with everything. But yeah, this is not published, so I'm actually waiting to discuss with my colleagues before, because I don't want to say something completely wrong, crazy.
We see at the end this response of the phytoplankton to this ring. This is more.
The sketch?
Yeah, like this. This is this before. This peaks. You have this is within a day.
No,
But this is a year.
No, the pigs, the pigs,
pigs.
the pigs
This
are,
is
7
1 month.
days.
This
Oh,
is
7 days.
This is
First is January, second is
every
February.
7 days. Seven.
Okay.
It's a very good right,
right,
the day,
I was thinking about
yeah, the way the spectral analysis.
Yeah. 8 January, it is 1st of August.
The reason the written
English.
for us,
Yeah,
because
this is because in
July.
US they do
Not the same.
opposite, and I'm used to do it like that. Because if not, they always are confused.
So deep is maximum.
But the interesting is these two frequencies. We have this 7-day frequency and we have a daily frequency. But this can be maybe a metabolic thing, I don't know. But you can see there are these lines. There is a daily variability of
It
plankton.
is weird that
I don't know if it's day, night, or
you have
I don't know.
this daily fluctuation acts on the full water column. I mean, from 0 to 150. So it should be a strong event, something, not a light breeze or something. It should be something important.
Maybe it's a metabolic thing, no? I heard about that when the plankton goes deep and there is not much light, they have more chlorophyll.
Produce more chlorophyll.
I don't know what's the name of that. Do you know, the biologist? This photo adaptation? I don't
Yeah,
know.
but how can in one day go a phytoplankton go
To 100 meters, it's a lot.
It might be only the different response to the sensors. But the concentration of chlorophyll should be the same in 1 day.
It's not that the plankton goes 100 meters up and down, it's that it increases daily. It's not necessarily moving, it's just increasing and decreasing. It's this. It's lines like that. It's
If it is night and day, then it can be light predation, then during the day it grows.
It's what some people told me, that what I need to do to remove this daily variability, it's just consider the night profiles, do the same plot, because here are night and day profiles. So they told me just do the same plot with day profiles or night
Yeah,
profiles
I will try.
and see the
You
difference.
have not oxygen anyway.
Yeah, we have oxygen
Yeah,
data.
because this is also interesting if you see variation on the oxygen.
I have there the oxygen.
Because not there should be in some way, if it's due to variation of phytoplankton and day and night, you should maybe see.
Yeah, I don't know if I have this plot there. No, I don't have it.
And also my question was if the oxygen, where was the oxygen, is saturation, where was if the peak was a little bit above the chlorophyll maximum, or
I think it was also distributed like looks.
No, I mean, when you have not the mixing condition, but when you have the
winter.
summer condition, where is the oxygen maximum oversaturation, let's say, if it's a little bit above the chlorophyll maximum, is usually or not. This will be my question.
I just remember on winter that was well distributed also, like the chlorophyll looks resembled to the chlorophyll, but I don't remember.
Anyway, comparison if you have oxygen is very useful.
Yeah, I can check now. You can maybe tell me more about the oxygen distribution.
We can, I would suggest it is very nice input for maybe that we can discuss as a science for on Wednesday. Get a little bit brainstorming to these issues, and then we get some notes, and then we can discuss about this. Maybe you can get also the oxygen if you can get that, then we can present and we can talk and just have a little bit brainstorming and so on. Yeah. Okay. Any questions? No.
There is the coffee break.
There is a coffee break, and then we resume as soon as we can connect with Mexico. That is 8 o'clock in the morning. I just wait. I have to close the.